If you mix charcoal powder with sulfur and a third specific ingredient, you obtain gunpowder. The first two are easy to find. Burnt wood turns into charcoal. Sulfur exists in volcanic mines scattered throughout Europe. But the third component, saltpeter, represents 75% of the mixture and determines whether the gunpowder will explode or just burn slowly like a common campfire. Then comes the question that has terrified generals and kings for centuries. Where does saltpeter come from when there are not enough natural mines to supply entire armies? And since we are talking about things that explode, subscribe to the channel before the explanation gets even stranger. Because the answer to this question involves latrines, and you will need to be prepared. The answer is not underground. It is in latrines, stables, the damp walls of basements where human and animal urine accumulates for months. Saltpeter, chemically known as potassium nitrate, does not need to be mined. When you understand that it forms on its own whenever organic matter decomposes in contact with lime and in the presence of certain bacteria. The problem has never been the scarcity of raw material. The problem has always been convincing an entire population to hand over their waste to the state, turning filth into white crystals, and doing this on an industrial scale without knowing a single law of modern chemistry. In the 18th century, no chemist could explain why it worked. They only knew that it worked. Louis XIV's France had technical manuals detailing every step of the process, but none of them mentioned bacteria because microbiology did not yet exist. They worked in the dark, guided by empirical recipes passed down from master to apprentice, and still produced enough saltpeter to keep cannons firing and muskets shooting in all the European wars of the time. The gunpowder that decided battles was made with what society discarded. And it all starts by understanding that decomposition is not the end of a cycle, but the beginning of a chemical reaction. When urine and feces accumulate in a closed, humid space, specific bacteria begin to work. These microorganisms, invisible to the naked eye, break down urea and other nitrogenous compounds present in waste and transform them into ammonia. Ammonia, in turn, is oxidized by other bacteria into nitrite and then into nitrate. This process is called nitrification, and it happens naturally anywhere there is decomposing organic matter, constant moisture, and a source of alkaline minerals such as potassium or calcium. The 18th century did not know these microbiological stages, but it knew the result. White crystals that formed on the walls of old stables, in poorly ventilated basements, and in piles of manure mixed with ashes. Nitrate needs a partner to crystallize. Alone, it remains dissolved in the moisture of the environment. But when it finds potassium, usually coming from wood, ashes, or quicklime mixed with soil, it forms potassium nitrate, saltpeter. The reaction is simple in chemical terms. Nitrate ions bind to potassium ions in a stable crystalline structure. However, for this to happen in sufficient quantity, it is necessary to create a controlled environment. The so-called artificial niter beds were huge mounds of earth mixed with manure, urine, ashes, and lime, kept moist and periodically turned to ensure aeration. These stinking mounds were true primitive bioreactors where bacteria worked for months transforming organic waste into military raw material. The logic was brutal and efficient. The denser the urban population, the more waste, the more concentrated waste, the more nitrification. The more nitrification, the more saltpeter. Large cities like Paris, London, and Amsterdam became involuntary factories of potassium nitrate. The state did not need to mine saltpeter in remote places. It only needed to collect what already existed in the foundations of the houses themselves. Royal inspectors had legal authorization to enter private properties, scrape basement walls, collect soil from stables, and confiscate compost heaps. Modern warfare literally depended on a nation's ability to process its own filth, and whoever mastered this dirty chemistry dominated the battlefields. Now you know the secret. Bacteria eating poop generate explosives. Beautiful, poetic, but there is one detail. Someone needed to collect tons of this foul raw material, stack it, water it with more urine, wait months, and turn it all into white crystals without exploding in the process. And no, there was no occupational safety manual. If you think understanding chemistry was heavy, just wait until you see the step-by-step of those who got their hands dirty. Literally. Subscribe now, because the continuation is the complete tour through the most disgusting and genius factory in history. The process began with the collection. Teams of workers roamed entire neighborhoods equipped with shovels, buckets, and carts. They scraped the soil from stables where horses urinated daily, collected the dark and moist earth from hen houses, and removed entire layers of sediment from the bottoms of public latrines. This raw material, laden with crystallized urine and decomposed dung, was transported to open yards on the outskirts of cities. There, everything was stacked in mounds that could reach the height of an adult man. The pile was not random. Alternating layers of manure-rich soil, wood ashes, quicklime, and straw formed a structure that allowed air circulation and moisture retention. These mounds were periodically watered with fresh urine or brackish water to maintain intense bacterial activity. After 6 months to a year of fermentation, the soil was saturated with nitrate. The next step was leaching. Workers dismantled the mounds and transferred the soil to large wooden or stone tanks. Hot water was poured over the material, dissolving. The nitrate salts present in the soil. The resulting liquid, dark and pungent, flowed through holes at the bottom of the tanks and was collected in containers. This broth, called mother liquor, contained calcium nitrate, potassium nitrate, magnesium salts, and organic impurities. To isolate pure saltpeter, a chemical purification process based on solubility differences was necessary. Potassium-rich ashes were added to the heated liquid, causing calcium nitrate to react with potassium carbonate, forming soluble potassium nitrate and insoluble calcium carbonate, which precipitated to the bottom. The purified solution was then boiled in iron cauldrons until most of the water evaporated. White crystals began to form on the surface and edges of the container. These crystals were carefully removed, washed in cold water to remove residues, and left to dry in the sun. The final result was saltpeter with a purity exceeding 90%, ready to be ground and mixed with charcoal and sulfur, in the exact proportion: 75 parts saltpeter, 15 parts charcoal, 10 parts sulfur. The gunpowder was complete. But the journey to this point involved tons of human waste, months of waiting, exhausting manual labor, and an empirical knowledge so precise that minimal errors in dosing or fermentation time ruined entire batches. The chemistry of the 18th century did not understand bacteria, but it understood proportions, temperatures, and reaction times with a precision that defied the theoretical ignorance of the time. Nitrogen is the central element of this entire story. It represents 78% of the air we breathe, but in this gaseous form, it is completely useless for most living organisms. Plants cannot absorb it directly. Animals cannot metabolize it. The only way to transform atmospheric nitrogen into something biologically useful is through processes that break the extremely strong triple bond between the two nitrogen atoms in the molecule. In nature, this happens in two ways: lightning during storms and the action of nitrogen-fixing bacteria in the soil. But when we talk about saltpeter, nitrogen has already passed through human and animal bodies, been excreted in the form of urea and uric acid, and now needs only to be oxidized by specialized bacteria that live in environments rich in organic matter. These bacteria belong to genera like Nitrosomonas and Nitrobacter. The former transforms ammonia into nitrite. The latter transforms nitrite into nitrate. Both need oxygen to function, which explains why the nitrate beds were constantly turned over and aerated. Without oxygen, the process halts. Temperature also matters. Between 15 and 30 degrees Celsius, the bacteria work at an ideal pace. Below this, nitrification slows down. Above this, especially in very hot climates, excessive evaporation kills off the bacterial colonies. The pH of the environment needs to be slightly alkaline, between 7 and 8, which is why lime and ashes were constantly added. In acidic environments, nitrifying bacteria do not survive. The 18th century did not measure pH with indicator papers, but it knew that sour earth did not produce saltpeter, while sweet earth mixed with lime produced crystals abundantly. The crystallization of potassium nitrate depends on a physical property called differential solubility. Potassium nitrate easily dissolves in hot water but precipitates quickly when the solution cools. Calcium nitrate, on the other hand, remains dissolved even at low temperatures. This difference allows for separation. When potassium ashes were added to the heated mother liquor, calcium reacted with potassium carbonate forming calcium carbonate, which sank like a white sludge while potassium nitrate remained in the solution. When the liquid cooled, only the saltpeter crystallized. It was not magic, it was solid-state chemistry based on differences in bond energy and temperature. The artisans of the 18th century learned these rules by testing, failing, adjusting, and repeating over generations, creating a body of technical knowledge as sophisticated as any modern manual, but without a single equation or scientific name to justify it. The saltpeter industry reveals something disturbing about the history of science. You do not need to understand why something works to make it work perfectly. For centuries, Europeans produced tons of potassium nitrate without knowing that bacteria existed. Antoine Lavoisier, the father of modern chemistry, only identified nitrogen as an element in 1772, decades after France was already operating state niter works on an industrial scale. Louis Pasteur's germ theory would only come in the 19th century. But this did not prevent entire generations of workers from mastering fermentation times, lime proportions, leaching temperatures, and crystallization techniques with a precision that rivaled contemporary laboratories. Empirical knowledge, transmitted orally and through practical demonstration, surpassed scientific theory for at least 150 years. This mismatch between practice and theory had profound consequences. Countries that controlled the production of saltpeter controlled their military destinies. England, surrounded by seas and without large natural deposits of nitrate, depended on imports from India, where mineral saltpeter was abundant. France, unable to import during naval blockades, invested heavily in artificial niter works and created legislations that forced citizens to deliver waste to the state. Prussia developed extraction methods so efficient that it could produce gunpowder cheaper than any European rival. The geopolitics of the 18th century was largely a struggle for control of the nitrogen cycle, even though no one knew how to name this cycle or describe its biochemical steps. Wars were won not by those with the best generals, but by those with the best manure processors. The true paradox lies in the fact that the technical solution preceded the theoretical problem. 18th century chemists did not ask, how do nitrifying bacteria work, because they did not know they existed. They asked, how long does it take for this earth to produce crystals? And what proportion of lime maximizes the yield? These practical questions generated accurate answers, detailed manuals, specialized craft corporations, and a complete industrial system, all without a single hypothesis about microbiology. Only in the 19th century, when science finally caught up with technique, was it possible to explain retroactively why those absurd methods of stacking dung and watering with urine worked so well. The gunpowder that shaped the modern era was born from humanity's ability to observe, repeat, and refine natural processes without fully understanding them. And perhaps this says more about progress than any theory ever could. So next, time you hear about scientific innovation, remember, Before Einstein explained the universe, someone had to explain how to turn shit into firepower. And it worked.